looking at position. It's part of our section on motion in one dimension. It's very exciting, so let's just get right into it. So, have you ever thought about this? Is it possible to run a race and yet have gone nowhere? And I don't mean running on a treadmill, but actually on the road, running a race, running around the suburb, and yet in science terms, you've gone nowhere. That sounds a bit weird, but it is possible. So we're going to talk about that. All right, so we've been looking at motion in one dimension. We've looked at vectors and scalars, and we're now going to look at frame of reference and position today. So here we go. Here are our keywords. Frame of reference, that's very important, which is a new term. Position, distance, and displacement. Those three, but position, distance, and displacement are related to each other. And we're going to see that today. So let's look at frame of reference. When we look at the frame of reference, we have to look at what the definition is, okay? And defining a frame of reference feels a little strange because it's not something we normally do, but you actually do it instinctively in that you always look at the world from a certain point of view. And that's what we're talking about, is we're going to define where we're looking at the motion from, because that's really important for us to describe it. So we're looking at motion in one dimension. We're going to look at movement in one plane. In other words, what I'm telling you is when we look at motion in one dimension, I'm only going to look at things that go backwards and forwards, horizontal, okay, or things that just go up and down. We're not going to take something that's going to go at an angle. Not yet. We'll add that in later. So motion in one dimension means one plane, one parallel motion, okay? So backwards, forwards, up, down, not together though, okay? Which is what I've just told you. So when we look at frame of reference, this is our definition. It's a reference point. So the frame of reference is the point from which the position of an object is measured. So if I want to look at me to my screen behind me, I can be the reference point, okay? If I'm considering me to the camera that's in front of me, I can either go, I'm the reference point, or the TV, the screen is the reference point. I have to know where I'm measuring the distance from so I can describe it properly, okay? It's the same as when you give directions. You sometimes go, no, just turn left, then turn right, but you've got to tell them where. And you've got to tell them relative to what. What are we looking for, okay? Ooh, there we go. Let's look at position, displacement, and distance, because they go together. So position can be described as a displacement or a distance. Displacement is a vector. So when I look at displacement, it's actually how my position has changed compared to the starting point. So have I gone 20 meters to the right of where I started? Have I gone 30 kilometers north from where I started? So displacement is how the position changes. Distance, I don't care how you did it. Distance is, I went 20 meters. I went 30 kilometers. Okay, distance doesn't care about which way we went. And that's actually how races work. You can run a half marathon, heaven forbid, 21 kilometers, but if the start line and the finish line is in the same place, you may have run, or in my case, walked 21 kilometers, but you start and stop, you actually have zero displacement. So in science terms, you did nothing. This is why I don't like running. Okay, so position is the place where an object is relative to a reference point, where we're measuring it from. Distance is the length of the path followed by a moving object. We don't care how it gets there, okay? Displacement, here we go, is the difference in position with respect to the starting point. That's the important thing here. We need to know where the starting point is. I need to know where did I begin. Because if I know where I began, then I can get to an idea of where I'm going, okay? It's the same thing as when we go, I'm hoping you've heard this saying when somebody says, as the crow flies, it's 20 kilometers away. And you're like, okay, what does that mean? That means if we could fly over all the buildings, it would be 20 kilometers. In fact, when satellite navigation and GPS things first came out before we had them on our phones, it was very frustrating because the directions they would give you, and they'd say, okay, you've got to go 30 kilometers, it's going to take you 10 minutes, because they would always go how far, like if I could just jump over all the buildings, I'd get there, it would take 10 minutes, but we can't. So I often had to put extra time on there. Phones are much better now. Plus, they can tell us traffic and all sorts of things, okay? So, we've now covered frame of reference, position, distance, displacement. We're going to look at all four of those in lots and lots and lots and lots of detail. And we have to get into our heads the difference between if I'm saying position or distance or displacement, okay? So, time for a short break, and I'll see you in a couple of minutes. Welcome back, everyone. We're still busy looking at position and frames of reference, and distance and displacement, but let's look at that in a little more detail now, okay? So let's really get into the nitty-gritty. Here we go. So we're going to consider someone's path during a walk. So a friend of mine sent me she did a walk, she sent me her distance thingy that her fitness tracker gave her. So here we go. This is the walk. Now, if we look at this, we can see that she started where the 4.39 kilometers is, and then she went for a walk and followed this very strange little path. It almost looks like a square, but not quite, okay, and then ended up where she started. We're not going to worry too much about how slow it was, because that doesn't matter. And you see, don't want to know how slow it was. So if I had to describe, this is like the race we were talking about, in that started and stopped at the same place, but followed all sorts of directions. So went up, turned a corner, went up. And if I had to now describe to you the path that was taken, it could be anything. I could say she walked 4.39 kilometers. Maybe she went straight for that time, or maybe she went straight for 2 and then came back, or who knows, okay? So here it's about describing where she is from a starting point, okay? So let's have a look at that, and we go, well, if I use left, right, up, and down as my direction, so we're going to say, we've got over here, so she starts, okay, actually, I think I need to use this one. So this is my starting point over here. Okay. Now, first of all, I'm going to say, I'm not going to use up and down on the board as left and right because it's an angle. So what we're going to do is we're going to make that left. So we're looking at it from an angle, okay? So that's the left direction, and that will be the right direction, okay? Just to give us a reference point. So now if we look at this, she went up a little bit, and that's probably about 50 meters. So what we would say is, if we had to describe this, we could say, well, she went 50 meters up from her starting point, okay? So she went up 50 meters. Then she turned a corner. Now she went to the left, and that's a short little distance, so let's say that's 10 meters. She then went 10 meters left. All I'm giving here is distance. I'm not saying relative to anything. We're just giving distance. Here, the point with this is that it's a distance. I'm telling you where she went, which makes it a displacement, because I'm giving you a distance and a direction, but the direction is here. So this first displacement is from her starting point, okay? Let's do that. This one is from the second point, okay? So it's not from the starting point anymore, which means she's going to have a displacement. Now, this is quite small, so we're going to use that just now. Then she walks along and she goes up, and then she goes to the left, then she went up again, and then she goes to the right and she gets here. Now, according to the fitness tracker, she's now done 1 kilometer, okay? But that 1 kilometer is a distance. She's physically walked 1 kilometer. Distance, she's tired now, but that's not her displacement, because that distance is from her starting point, okay? But if I had to describe what her displacement is, so she starts here, and if I had to go, well, she's actually there, okay? So she's walked 1 kilometer, but if she could have jumped over all the houses that are here, which we can't, and it's a good thing, okay, what I would actually say is from here to here, whoopsie, again, here to here, that's her displacement. And if we look at it, it's not quite up. It's not quite directly up, okay? Now, I said to you that we were going to look at motion in one plane. And now you're going, but Tracy, you're going left, right, up, down. I'm still in one plane because she's on a road. So the road can change direction, okay? But it's still one plane. I'm not changing. So she's not going at an angle in her motion, okay? It's still flat. Her displacement is definitely not 1 kilometer, okay? And looking at this, her displacement's probably about 400 meters, okay? And that, if she could have walked from here, see, it doesn't like this, from here to here, okay, she would only have to do 400 meters. Now, we could have done that a lot faster than the 1 kilometer, because if you look down here, this time is telling me it's averaging 10 minutes and 53 seconds a kilometer, so it's about 11 minutes, okay? So it takes her, that's very slow, by the way. But this is a distance, okay? This red one, it's a displacement. So I would have to describe that displacement as 400 meters up. So that's from her starting position. My frame of reference is there. I can change my frame of reference. So if we now go, let's make that 1 kilometer her frame of reference, okay? So from this point, we're now going to look and go, well, from that 1 kilometer point, she went to the right, okay, for how many meters that was. Then she went down, okay, and then she went to the right again, okay. Now she's got another kilometer. So we've traveled a distance of 1 kilometer, but her displacement, now here, because of the way it was done, it's probably going to be close to 1 kilometer, but it's not, because her displacement is from there to there. It should be a straight line. So again, displacement ignores all the twists and turns, okay? Displacement is a straight line. Distance can take twists and turns, and we don't really care. Displacement is a straight line from one point to another. If we're now looking at her displacement from the starting point, it's there to there, okay? Let's now consider, and there's lots of things written all over here, so let's just take some of this out because it's going to make it a bit easier in a second. When she gets to 4 kilometers, so she gets here, and at this point she wants to fall over because it's been long, okay? That point here, she has walked a distance of 4 kilometers. In that distance, she has gone up and down and round and right and left, but her displacement is from here, oopsie, to there. It's very short. So instead of doing that whole 4-kilometer route, if she wanted to get here, she could have just gone, and that's probably about, we're just going to pretend probably only 500 meters or so. No, yeah, it's not even that, but we'll make it 500 meters. So instead, she could have gone 500 meters slightly to the left and down, okay? Right, that's right. Left and right, very important. Slightly to the right down, and she would have ended up in the same position. Why can't I do that? Because there are roads and houses and things in the middle, okay, and we can't jump over them. With this one, describing this as left, right, up, down feels a little clumsy, okay, because we're doing lots of turns. What we could do instead, is instead of using up, down, still the same thing, we're going to use the cardinal points. In other words, north, south, east, and west. Here I need you to pay attention, because when we look at a piece of paper, we automatically, it's ingrained in us, we go north must be up. So we want to go north is in this direction. But it doesn't have to be, and I've done this deliberately. So I know from this map, all right, that north is actually there. North points this way, okay? This is a street map. I don't have to twist it so that it goes north up. Be careful. If we are going to give you displacements and distances where north isn't straight up, I have to tell you where north is, okay? Do not make the assumption. It also means, and this is what I wanted you to see, I, in the last diagram, gave you down like this as being left. We also tend to go, I'm always looking north, which means right must be east, left must be west. That's also not true. You cannot make that assumption. I'm telling you that we're going to use the cardinal points, north, south, east, west. So if that top part is north, then there's east, there's south, there's west. Okay, we know which way it goes, okay? And you can remember it as being never eat salt water. I don't know, whatever. Okay, so we look back at my displacement. So let's go from here to here. That's 2 kilometers, that distance. But if I look at her displacement, this is actually better to describe, because if I put my north-south lines here, can you see that she's southeast? Not quite southeast, because here's north, all right? But if that's the east line and that's south and that's east, if I could find that angle, which I could measure if I had a protractor and I did this accurately, I could describe that distance as being, and that's probably about 1 kilometer. She's 1 kilometer, and we could do it as a bearing, so let's just do it as bearing. We've done that before, and I'd say she was 1 kilometer bearing, looking at that angle, 160 degrees. That is far more accurate for me as a displacement, far more accurate, because I can tell exactly where it was, whereas the left, right, up, down doesn't really help me. So sometimes the cardinal points are a much better indication of where I am, okay? Even if we now go to the 3 kilometer mark, which is over there, okay, and that's definitely further than 1 kilometer, but you can see almost that now the angle she's gone, there's a degree, it's a different angle. So that bearing is now bigger than 180. It's probably about 200, okay? I know that you're looking at this and going, how are we going to tell, Tracy? Don't worry about it. This is just a case study. This is just to help you understand the difference between distance and displacement, okay? Of course, we have to have our reference, where we're starting from, okay? We need to know what we're comparing it to, and then we can go from there. So it makes life a little bit easier. Your questions will be better than this, okay? This is just very complicated, but I wanted you to see it in terms of something that's more real world for you, okay? So, distance measured with a pedometer or an odometer. Pedometer is like your fitness trackers, okay? Odometer is what's in a car. It's the total length. Direction doesn't matter. The symbol is D for distance, and its unit is meters, and it's scalar, okay? Displacement, shortest distance from between start and end. Direction is important. Direction is measured from the starting point. It's always start to finish, always includes a direction. The symbol is either an X for horizontal or a Y for vertical. We will look at that again. This is because we can change position, and its unit is also meters. I know I did some examples with kilometers, but we will always change to meters, okay? And it's a vector, so it can be positive or negative. We will look at that. Well, guys, that's all for now. It's time to take a short break, get refreshed, and I'll see you in a couple of minutes. Welcome back, everyone. Now, because we understand position and distance and displacement, now we need to do some calculations. So, two cars are stopped at a robot. One car starts moving. You are in the stationary car. So now we're going to say, what is your motion relative to the moving car, and what is your motion relative to the robot? So, two cars. I can't draw, so just go with it. So we have your car. Okay, there's my car. I teach science for a reason. Okay, and then we have another car. These are box cars from a long time ago, and gratefully no cars look like that. So you're here, and this car's not moving. This is stationary. This car starts moving, and I want to know, what is your motion compared to this one? And I know most of you are going to say, no, we're stopped. Actually, if I'm in the moving car, and I look at your car, which isn't moving, I'm going to be going forward, you're going to look like you're going backwards. So your motion relative to this car that's moving forward is actually backwards. Okay? You're going backwards compared to the car going forward. If I was using the stationary car as my reference point, then the moving car is going forward relative to the car. Okay? So what am I saying to you? Frame of reference, very, very important. Where am I comparing it to? All right? The second question is, what is your motion relative to the robot? So we have my stationary car, which has changed shape. Okay, and here's the robot. Okay. Robot's not moving. We're not moving. So your motion is nothing. Your distance isn't changing. You're staying in one point. So now, if I'm comparing my motion to something that's stationary, I'm stationary. Feels a little weird, okay? But don't worry, you'll get there. So, you're sitting in a train which is moving at 30 meters per second north, what is your motion relative to the train? What is your motion relative to the train station platform as the train goes past? So, you're in a train. Here's my train. I'm not even going to put wheels on. And you are here. So you're sitting in the train. There's your chair. Okay. You're just sitting there. The train is going at 30 meters per second. And it's going north. I ask you, what is your motion relative to the train? Well, if I'm just sitting in the train, my motion is 0. According to the train, I'm not moving. I have 0 meters per second. I'm not going anywhere, okay? I know that if I combine myself with the train, I'm moving, but the train has become my reference. And for me, if I look at everything in the train, I'm going nowhere. I'm 0, okay? My motion is stationary. If I now go relative to the train platform, so now we still have our train, okay, you're still sitting in your train, there's your chair, okay, and that's his, whatever, you're reading a book. Okay, can't draw, we know this. Train is going at 30 meters per second north. Now, essentially what I'm asking here is if you're in the train and someone on the platform is now watching the train go past, you're moving with the train. So if I'm watching from the platform, your motion is now 30 meters per second north because someone outside the train is watching. Where my frame of reference is has changed. Okay, so now you are moving at 30. Oh, now we're still sitting in the train, going at 30. You now stand up and walk north on the train at 2 meters per second. What is your motion relative to the train? What is your motion relative to the stationary train station? So, the difference is now we've got the train. Train's moving at 30. And now you decide that you need to go for a walk. Inside the train, you are going 2 meters per second north. When you were just sitting, your motion was 0. Now you get up and you start walking. So think about it this way. If somebody was sitting in the train and now watched you walking, they would go, you're walking 2 meters per second north relative to the train. Because we're not worried about what's going on around the train, we're worried about what's going on in the train. So your motion would be 2 meters per second north relative to the train. Okay, that's my frame of reference. Now they want, what about the person on the train station? Well, here's the train again, going at 30. Here's you going for a walk at 2. Now this one's fun, because what's the person going to see? The person's going to see the train come past at 30, but at the same time there's someone walking in the train going at 2. That person is actually going faster than 30. The person's going to be going 32 meters per second north. Remember, that's relative to the platform now, okay? Platform. There we go. All right, so my cat loves to sit on the windowsill in my lounge. One day she saw a mouse that was 1.5 meters to her right and a toy ball that was 2 meters to her left. So this is the situation. There's my cat, there's the mouse, there's the ball, okay? If I now want to describe her, she's my reference point. So I would say the mouse is 1.5 meters to the left of the cat, okay? But if I go, what is the mouse relative to the ball? the mouse is now 3.5 meters to the left of the ball. Now that's quite important. I need to know where I'm measuring it from as to whether I'm going to say the mouse is at a distance of 1.5 or the mouse is at a distance of 3.5, okay? And it's a toy mouse, okay? I don't have real mice in my house, okay? There's no mice in my house. It's a toy mouse. It's her favorite toy, okay? But if I had to say to you, my cat decides to go play with her ball, which position-wise is 2 meters to her right. But being a cat, she's not going to go in a straight line to the ball because that's not what she does. What she does is she goes for a walk around the lounge and she goes backwards and forwards, and then she decides she's going to go play with the mouse for a little bit, eventually gets to the ball, okay, because she's running around having what I call her zoomies, right? But eventually she gets there. Now, that distance that she's traveled through all of that, that could be, knowing my cat, 10 meters, okay? So that would be her distance. But in reality, she's really only gone 2 meters right. She's just taken the long way around because she was having fun. And then she can start playing with the ball, okay? But she doesn't have to go straight to the ball. But in science, we don't often really like distance. We prefer displacement. It's just easier for us, okay? So, lots that we did. So we've looked at relative motion from our frame of reference. We've looked at displacement, okay, with my cat. We've looked at describing the displacement from a starting point and distance from a starting point, okay? And I'm hoping it's all starting to make a little bit of sense for you, all right? So we're going to take a short break, and then we're going to do some more calculations. So I'll see you in a couple of minutes. Welcome back, everyone. We're going to do some more calculations. Now we're going to start doing a little bit more the sort of calculations you're going to get in tests and exams, okay? So, a bird flies 100 meters east. Then it flies 60 meters west. So the questions are: represent the movement in a diagram. What distance did the bird fly? And what is the bird's displacement? Now I'm bringing in stuff that we've done before and we're combining it. So here we go. We want it as a diagram. So this is not to scale. This is just a sketch diagram. So the bird flew. I'm going to make that north, up, okay, so I know where north, south, and east is. And they tell me that the bird flies 100 meters east. So there's my 100 meters. Then it flies 60 meters west. So it goes this direction, 60 meters. We've got the diagram. We've represented it in a diagram, okay? So now they say, what distance did the bird fly? I'm just going to put the diagram again to make it easier for us. So there we've got the 100. There we've got the 60. It's not to scale. Distance simply means that I add everything together. So I'm going to go 100 plus 60, 160 meters. Because that's what the bird actually did. It went 100, then it went 60. That's its distance, okay? And it's tired. It went 160 meters. Now they ask us, what is the bird's displacement? If I drew this with a scale diagram, so there's my 100 meters, there's my 60, I know now that her displacement, I'm calling it a her, is from the start of the first one to the end of the last one. And hopefully, you guys can see that that would be 40 meters. Okay, and in which direction? Because we know originally that was east. So her displacement, which we're going to call delta x, because she's changing direction in the x value horizontally, is 40 meters east. But what if I told you that I didn't want a diagram? That I want this done with a calculation? I mentioned earlier that displacement is a vector. Because it's a vector, it can be described as a positive or a negative. So I have to choose a direction to be my positive direction. I'm going to take east as my positive. Why? Simply because it was the first direction given. Sometimes we're going to tell you what direction we want as positive, but most of the time we're not. You must choose one that makes sense to you. What I like to do is always choose my first direction as my positive direction. Because if I do my calculations the same way every single time, I'm not going to get confused. So I'm not going to spend time going, ooh, which direction must I choose? First one mentioned. It doesn't matter if your answer ends up being negative, because you can work out what that means, okay? So that means for me that my first distance, okay, was 100 meters, and that's positive. My second distance was 60 meters west. That makes it minus 60, okay? That minus isn't a negative number like on the number line. That minus tells me I changed direction. So that minus is important. To calculate my change in x, I need to take my first distance and I need to add it to my second one. So I have 100 plus minus 60. Now, if you need to use your calculators, use your calculators. I can do 100 minus 60. So I get 40 meters. I get a positive answer. That means that this is 40 meters east. I wanted displacement. Displacement is the change in position. So I want to know where the bird was relative to where it started. So I could tell someone, go find the bird. The bird is 40 meters east of where I am now. They can find the bird, okay? They don't need to go 100 and then 60. They can just do the 40. So a group of friends go on a hike. They first walk 60 kilometers west. They rest a little bit. Then they go 10 kilometers east. They rest again, and then they go 4 kilometers west. Sure, it's not something I'd want to do. I'm going to be honest. So, first question, calculate the distance covered. Distance, I don't care. So they've gone, west, let's make west that way. So they went 6 kilometers. Then they went 10 kilometers. And then they went 4 kilometers. Okay? And we can hopefully all do this, but they want distance. Distance means I'm going to go 6 plus 10 plus 4. Okay? We like questions like this because this is nice, easy maths for us. Okay? If you need to use your calculator, then let's do that. Okay? So let's put it over here quickly. So we've got 6 plus 10 plus 4, and we get 20 kilometers. Now note, I haven't told you how long it takes them to do this, right? I'm pretty sure if I was doing this, I would have rested way before the first 6 kilometers. But that's distance. Now, okay. Oh, there it is. I lost where that went. So, wrong way. There we go. Now they want the total displacement. Displacement means I need to choose a direction as positive. I said to you just now, we'll take original direction as positive. So my first one is 6 kilometers, and I'm taking west as positive. I like to write down what I'm taking as positive to remind me. My second distance was 10 kilometers east. East now becomes my negative direction, so that's minus 10. We're going to go, third one is 4 kilometers west. All right, so my displacement is my 3 positions added together. So it's going to be 6 minus 10 plus 4. So let's see what happens now, okay? So let's put this over here, and we've got 6 minus 10 plus 4. Oh, look there. Gives me 0. What does that mean? Now, first of all, we get 0 kilometers. This means they ended where they started, okay? I can't give a direction to this because they've gone nowhere, all right? So they really walked 20 kilometers for nothing. I would have just stayed there and waited for everyone to come back, okay? So their displacement, their change in position is 0. This is going to become important when we get to velocity and speed, okay? So calculate their position at the second stop. So they would have gone 6 kilometers west, first stop. Then they went 10 kilometers east. You can't change which direction you want as positive. Okay, so right in the last part of this, we went west is positive. I have to stick to that. You can't change your mind along the way. So we've still got west as positive. Okay, so x1 is 6 kilometers. x2 is minus 10. So changing x1, x2, 6 minus 10. Let's just make sure. 6 minus 10. Ooh, look here. I get minus 4. The minus means that it was going east. We can't leave it as minus. So x is 4 kilometers east. Doesn't matter, the negative just tells me direction. Okay? One last question. Aeroplane flies 100 kilometers east, 200 kilometers south, and finally 100 kilometers west. We want to know how far it flew and what its final position is. So if we go to the first one, how far did it fly? Far means, oh really? Far means distance. So distance, it went 100, then it went 200, then it went 100 again, so that's 400 kilometers, okay? We don't care about displacement. Then they say, what is the final position of the aeroplane with respect to the starting point? And it sounds more difficult than it is, because the plane went 100 kilometers east, then it went 200 kilometers south, and then it went 100 kilometers west. And hopefully, you guys can see that what we've done is we've created a rectangle. There's its displacement. It would be 200 kilometers south. I can't calculate this with positives and negatives because we went at right angles to each other. But I can still get the displacement because it's a nice diagram. okay? It's something that we can look at. It's geometry. It's things you've done before. They're not trying to trick you with something like this. I just need you to see that sometimes we can't just add them. We have to actually draw a diagram for them, okay? So, lots was done today, okay? Lots for you to think about, but we are done for this lesson. So, I will see you next time.